In this video, we are going to talk about something super interesting. So it's going to be about security, and we are going to talk about how we can hack chips. And I don't want to use this kind of word because basically we are going to talk about this topic because it's important for security. We would like to know if we are designing very important device which should be secure, or how other people possibly could maybe attack this, and how they could go inside of the board or of the chip. Is this what we are going to talk about, Dave?
Yes, that's correct. It's good to know what's possible because you can think about it when you're designing your own products. So, yeah.
So what kind of security issues we could have? Like very briefly,
Okay,
so people get
sure.
idea. Like maybe, oh, I'm sorry for
Yeah,
interrupting, but for me, it was very interesting when we talked last time. You mentioned, for example, if uses. People think they will use if uses to secure something, so no one can access, I don't know,
yeah,
flash memory, but it can be actually it's not as secure as we could maybe imagine. Correct?
yeah. Yeah, that's a good way to put it. Basically, anything that's checked in software, even hardware fuses need to be checked in software. So everything that can be checked in software can be attacked from the outside, from hardware side as well. And I think it's important to know because a lot of people will put big assumptions on features like secure boot or hardware fuses because it sounds hardware is secure. It's like something you cannot exploit like a software bug. But in reality, by having access to the hardware, you can change the control flow of a program running on an embedded device. And therefore, you can circumvent lots of security measures.
hmm So we are going to start with your demo, what you prepared. So talk a little
Yeah.
bit about this, and then we will go through. You prepared also a presentation where we will talk a little
Mhm.
bit more about details and how it works and what are the possibilities.
Yep.
This is
So
your logic analyzer.
yeah. So what we see here, first of all, in the camera, we have a target, which is this blue chip. Lots of you will know it. It's an Arduino Nano, and it's running a firmware that's counting up to a certain number. And we want to show how easy it is to change control flow with a simple MOSFET that's just plugged into the breadboard. So everybody can do this at home. And by performing a hardware attack, a voltage fault injection attack, we can change the number that the code is calculating. So
Oh, okay. So a little bit more because I
yeah,
still I don't understand. Can we see
all
the
right.
code, for
So
example? Can you show the code?
sure. Or it's easier if I describe it. The code is
Okay.
just a loop counting from 0 to 255.
Okay.
And by injecting um, a small glitch in the core voltage of the chip, we can basically pause the execution for a few nanoseconds so that a few instructions don't get executed. This is a demo to make it simple, but imagine instead of this being just count instructions, one of these is an important check or readout of an if-use value. So let's say all of your variables are initialized as 0, and you can glitch all of the readouts, then the variables will stay at 0. And depending on the code that you have, it will impact it a lot.
So
So
basically, we are going to skip some numbers.
yes, we are going to skip instructions that count numbers.
Mm-hmm.
And this is because it's easy to spot the difference
Mm-hmm.
there because we just need to glitch or hack one of these 255 instructions
Mm-hmm.
and not a very specific one.
Mm-hmm.
Um, so what we see here, it's also as a possible attack against the real firmware because sometimes they are locked in a state like this where it's an infinite loop. And there's even if there's no counting, if you can jump out of that loop, then you maybe get access to some some hidden functions like a console or internal settings and stuff like that. So it's not uncommon to lock users out by just sending them into an infinite loop in a production firmware, meanwhile keeping critical parts of the code in the firmware. And by doing such an attack like this, we can kind of jump to it. If we do the more advanced version of this, we can even jump to very specific addresses. And so this can get very sophisticated very quickly and very advanced. Yeah, I will just start my attack script. The attack script runs on this Raspberry Pi Pico microcontroller, so also inexpensive hardware. And it's just listening for a target trigger signal, which is not connected. But basically, the target will also, to make it even easier, it will tell us when it's starting to perform these calculations. So we can see here that the target calculates for 28.6 microseconds. And during this time, we want to attack. So if I start my attack script and I pause it again, I can show what's happening. So basically, the target starts calculating. So the Arduino is the target. It starts calculating numbers.
So it is in the loop or counting
yes.
0, 1, 2, 3, 4.
Yes, this is the whole loop, 28.6 microseconds. Okay. And we have this little blue spike here. And this is the MOSFET gate. So I just explained it for you as an electrical engineer. If you put a signal on the gate, it's an N channel, so it will switch. And in our case, it will bridge the core voltage of the Arduino to ground. And
so for a very short time, we will create short
we are
circuit
talking
on power.
about, yes. It's only a few nanoseconds in time, as we can see here. And
I have another question. So the green one, that's the whole loop, like from 0 up to 255. Yeah.
Yes.
And what is it doing in the other time when it is low?
In that time, it's just waiting. So
okay, I guess it also sends the serial
it's doing
output.
Other stuff.
Yeah, I see.
Yeah,
okay, I see.
Serial stuff.
Okay, that's the locked text.
Yeah, it's just random computations.
I just wanted to be sure this 28 microsecond, that's exactly the loop which we would like to attack.
Yeah.
Okay.
Yes, so this is another thing I did to make it easier to attack. Basically, I put a GPIO high and low before and after the critical operations. And you would always do this even on a real target, because usually you can get a dev board for it, for instance, and then you can program it with whatever you want. And you can add something like a GPIO trigger so that you know when certain things are happening during boot time. And then you can relate that on the real product where you don't have the firmware. Then you can apply all this knowledge that you have gained from the development board on the real thing.
Okay.
Yeah. But I don't want to get into too much theory right now. Basically, I just want to show how fast it is to attack this device on a simple setup like that.
So right now nothing happened, yeah? Right now nothing
happened. Right now I'm not doing anything. I paused it. And I will just restart it and let it run. The target it's just stuck in this loop where it's locked, because the value is always 255. It's as if we were reading a fuse, and the fuse has a locked value and we can't do anything about it. And now we try to modify this value. And yeah, this is maybe a better time scale. We are not hitting every target because the Pico is also a bit slow. It needs to be reinitialized for every try. So that's why I didn't bother optimizing or doing this more quickly. But
how do we know? There it is.
There it is. So we have detected volt injection count count value 254. So we skipped exactly one instruction, which is pretty nice because it's good to be precise. It means we can skip individual instructions in other firmware as well on this chip. So we know how to hack this chip now. We know that we need 290 nanoseconds and all the other
How
parameters.
do you know you skipped one instruction?
Because I programmed the target such that it outputs the count value in the end, and it outputs 254 instead of 255.
So now I'm
Yeah.
curious because the loop ends at 255, no?
Yes, yes.
But then how did you get the number 254?
So if I skip any of these, I have a loop with which basically I skip one iteration or one addition, but then it continues running. I didn't skip out of the loop. If I manage to somehow hit the wrong instruction in a sense, the loop instruction, then I jump out and I get something like 100. It can also happen. So I can run it again and
But
restart
so
it sometimes. Yeah.
are you counting the loops also outside of the loop, or that's what I'm would
Yeah,
like to
no, I
know.
have, imagine I have in assembly, I have a loop. I have, I need to reset the target. I have, let's say, a loop label, and then I have add register 0, 1, and then I
That's
have
what I was
jump back
asking
to the
about.
loop.
So the
So
value is
yeah,
there twice, two times basically. Yeah.
yeah,
The value is the
if
value of
I
the loop, and also you have some kind of addition.
yeah, I only have this addition register, and it means if I glitch the add instruction, then I get 245, like here maybe. But if I glitch the jump instruction, then I could exit the loop way earlier and get something like 50. So
Ah.
yeah, this is all stuff that you want to figure out as a security hardware security engineer to know what you're glitching. So this what we're talking about right now is something that's normal in the process when we want to analyze a target. We need to figure out what timing do I need to get the return instruction or to get the jump instruction by basically using what's almost a side channel like this firmware with the counter, because it tells us indirectly what happened.
Because right now you don't exactly know which instruction mm, you
Yeah.
skipped. Or
Yes.
basically you know based on the output from the serial console, but you can't really control it which one you are going to hit.
Yeah. Yeah. We could write the firmware in different ways to know. Like for instance, we could use multiple registers and try to only fault a certain one, like all instructions that affect a certain register and other instructions that affect other registers. We don't want to affect those. So in that case, we can like fine tune the timing even more. And for instance, we can figure out how much time from the boot up of the device until this critical instruction has happened. And yeah, it's a bit of trial and error in a sense, but guided trial and error. We also work on methods to automate this or to make it more efficient, but it's more complex topic.
If it's a 245, it means it skipped 10
Yes, it's now
loops.
now it skipped 10 entire loops or it skipped before the end. But as we can see here, yeah, it skipped 10 instructions,
Oh, because
150
it's not for
nanoseconds.
nanoseconds or
Yeah, it's too wide in this case, so
Mhm.
it skipped many instructions. If this pulse was further back, if it was somewhere here, it would be possible that we just returned early from the loop. But since it's this early, I know it just glitched 10 instructions.
So right now these pulses are like completely random width and random
Yeah,
place.
yeah, it's just to make it simple. I randomized the width and the delay and everything. And in reality, if I wanted to hit a certain instruction, I would like estimate it from the disassembly, from knowing the clock speed of the device. then from roughly estimating where it should be, and then I would sweep a certain range earlier, later, because of course we have physical effects. We have different clocks on the Pico and on this. They are not synchronized. So these are different factors to think about. And yeah,
But this is
that's
very interesting because this is actually saying not only about attacking the firmware, but this is also saying how sensitive uh, microcontrollers or processors can be for the voltage drop or something that basically your software may crash exactly because of this.
yes, definitely. So what we see the most on most devices, we see a lot of crashes because as soon as I do this too wide, the target will crash,
Mm-hmm.
and so I set some certain boundaries. And but you can get a lot of crashes, especially if you affect registers which have important values. If you return early and you have stack canaries or software measures that are usually made for integrity and stability and safety, you can basically trigger them inadvertently, and then you can crash your target, and then you have to wait for it to reboot, and it takes a lot of time. So it can be also annoying for the attacker actually. So a lot of security measures focus on making things annoying rather than making it 100% secure. Also, other people argue that you cannot make it 100% secure if somebody has hardware access, but at a certain point, it gets to a point where it's just infeasible
Mm-hmm.
to attack unless you have a lot of capacity, so a lot of time specifically to really find the perfect parameters. And I think that's the most secure countermeasure you can have.
Mm-hmm. But
Yeah.
also, what is interesting, basically, uh, if the pulse is too short, then the board will not crash. Only the one instruction can be affected. That's very interesting
Yeah, that's
because
what you want to achieve. Yeah.
yeah, because I would say like if the voltage drops, I would expect like the chip resets or something. No, it
Yeah.
doesn't reset. It continues.
Yes, yes, if it's only a very short time because you have capacitance, you have charge. So for board engineering, of course, we know about capacitance, heat coupling capacitors. So these can actually be a problem sometimes because they can hold so much charge that you need to make a really wide pulse for the chip to recognize it. And if you make it too wide, then your peripherals are gonna die because then your power supply is gonna like notice other parts of the chips are going to lose power, like registers, RAM, caches, all of that. If they lose too much energy for too much time, they will cause bit flips and errors, and the target will just crash. Yeah.
Hmm.
So
And just confirm. So you are shorting the core voltage, not the 3.3
yes,
volt
it's the core voltage because 3.3 is usually
for I/O.
um, yeah, it's usually too like if you remove core voltage, it's too drastic. You usually basically even if you do it very shortly, you will just reset the whole chip.
If you remove 3.3 volts, you mean?
Yeah, yeah, yeah,
Okay.
yeah, yeah.
But if you remove core voltage, it still may
Yeah,
continue working. You just keep the instruction.
that's correct.
Okay. And what chip you have on the other board? Is it STM or what is it?
The green
On the
one?
Arduino board.
This is the Atmega
Ah, okay.
328. It's old thing. It's yeah. As I said, it's mostly for the demo because it's super slow. It has 12 megahertz clock, I think. So it's good glitching target for demonstration.
And there are also different ways how we can do this, but that's what we are going to talk about in your presentation. This is only
Yes,
one of the
yes.
ways, or there is also a different way. Okay, I think now we can go to presentation, correct?
Sure,
The
sure.
demo
We
is
can come back to this if we need it.
okay. This is you know what is very surprising for me that the chip doesn't reset. That's like super interesting because as I said, even this also means if your
Yeah.
power rail is poor quality, then basically your board really may look like it's working perfectly fine, but no, it may not be working perfectly.
Yes. Maybe short thing about this. So there's actually a whole field of research basically that focuses on safety in this regard. So they analyze how do chips behave if they get blasted by cosmic rays or really to make sure that chips don't glitch by like environmental noises because this is also a possibility. So this can happen also if there's no adversary present. It can happen just because you have yeah, sun exposure like on space stations and stuff. So your systems may not crash, but you may have corrupted data in your RAM.
Hmm. Okay, so we can go at the beginning.
Yeah. So I start my presentation with this. It's just an assortment of hardware and this guy who's confused saying, what are we actually doing here? Why do we need all of this stuff? Um, yeah, I think this is maybe not so surprising for you, but for software engineers, they are often like shocked when they see that you need this much hardware to do hardware attacks. Um, but
You can
yeah,
explain what
uh,
is there. So what
yeah,
is there?
everything has a purpose. So we have CNC, of course. This is required if you do any kind of localized fault injection attacks like electromagnetic or laser, because you need to position your tool wherever you want to attack the chip. So if you imagine, I think I have pictures, yeah, like for instance here, we can see on the bottom right that there are spots where the attack fails and they color them red and spots where it doesn't fail where it's blue. So you need to move it automatically to automate the whole process. Then we have FPGA on the right of it. We have a Raspberry Pi Pico below it. We have a power supply connector board that you can see, which I made for resetting the target. Sometimes they reset through fault injection, but in a weird state. So some registers still have values and it's stuck in some sort of weird boot loop. So I need to programmatically be able to reset it in a clean state. So this is just convenient connectors, a MOSFET, and then I can use a GPIO to power cycle it completely
Hmm.
if needed. Above, I have a board for measurement of different signals so I can monitor the whole experiment. And below, we have a chip shouter. It's an open source EMFI device on the bottom left, which it's designed by Colin O'Flynn and built by you, so built by me in this case. And yeah, on the bottom right, you see again like my setup stuck together on a piece of 3D printed plastic with a breakout board, FPGA, and power supply breakout board with a MOSFET for switching. Yeah. Yeah. So we talked about it already. Basically, modern security features oftentimes prevent simple hardware attacks like extracting firmware or getting access to your own devices in a sense. If you want to get a root shell, install something else, you usually cannot do it. So um, this is one reason for doing fault injection attacks. And the other one, which we talked about, is just if you develop products, you want to know how secure they are or how to defend against attacks or what is possible. And yeah, here's some pseudocode where you can see we assume we have a static variable called debug enable. And in production firmware, you have this, you put it to false, and then you assume debugging is disabled, right? If we read this code, it says if debug enabled, enable debugging, and it's false. So software security or sorry, not software security, a software developer thinks, okay, it's safe, I can ship this. And in reality, I show this arrow first. The first one means if I glitch this assignment, then I can break this assumption, or I can glitch this compare instruction. So I have two spots here actually where I can glitch. And it's something you should know if you if you ship embedded devices.
But this is interesting because also you need to somehow know the code which is running inside, and usually, how do you get this information?
Well, in a real attack, there are some ways where you get the code, like you get it by dumping it or stuff like that. Although dumping flash memory usually requires a debug protocol, like yeah, if you need debug access, usually it's also locked. So yeah, but usually yeah. So if you can get the firmware, then you can read the code and really decide where do I want to attack and stuff like that. But if you don't have debugger access, then you kind of need to guess, or you need to use side channels. For instance, you can figure out when is crypto operation happening by monitoring power consumption. And yeah, but usually you need a hardware attack to get the firmware, not the other way around.
Yeah,
Yeah.
yeah, yeah.
This is just to show, I mean, it's similar with software attacks. Many times people write software in this kind of way, something like this, and assume there's no way to hack this, right? But what if a user inputs a different character? If they don't use ASCII, this is what fuzzing people use, for instance. So they try to break assumptions by not knowing what the code inside is looking like. And so we also need to have assumptions about the firmware and break assumptions of the firmware developers.
And this is also interesting because maybe does it mean like open source maybe more dangerous
Mhm.
because everyone knows what is inside, how the code should look, and then you exactly know where this is happening?
That's a good question. For instance, yeah, like in any case where you can get code or part of the code, it could make it easier for attackers. So let's say expressive ESP32 chips, um, you can hack their bootloader even if you don't know the firmware that's running on it, because the bootloader is in part on GitHub, or you can get it from a different device and you can analyze it and then you can know the timings. So mm if you have really full open source, then of course it's probably going to be easier to find the timings. At the same time, people can contribute fixes as always, and more people looking on it means more people who can help. So it's a philosophical question. And same as with software bugs or software attacks, same for hardware. If you publish the source, people can help you find stuff like this, and people can also use it for their advantage. So
Mm-hmm.
it's a two-sided sword.
Mm-hmm. Okay, I understand this.
Yeah, yeah, yeah. So
We can go next. Yeah.
if you want to fault something, or like if you want to attack something, you first of all, of course, you need to figure out what you want to attack. So is it a hardware fuse check, or is it something else? Because usually you have some sort of information, like you have a boot log, you have, as I said, the side channel for power consumption, or you just know that the chip is doing crypto. Like if it's transferring encrypted firmware from one device to another. Let's say Apple AirTags, they have one chip that boots the second chip, basically it transfers the firmware after it boots, but it's encrypted. So we know that the second chip, it gets the firmware, it decrypts it, and then it runs it. So this is something we know from prior analysis. And then from this prior analysis, um, we can know what to look for next. So in this case, we might want the power consumption side channel, but we could also reverse engineer the firmware. Of course, even if we have the firmware, reversing is always also hard. So it's not that easy that I can say, okay, I dumped the chip and now I know what to do. So yeah,
I'm just curious.
yeah,
Did you try AI to analyze, I don't know, assembly?
not not yet. I think people are doing that though. It's just not in my field.
Okay, it was just an idea.
Yeah. There's also research about AI for fault injection, I think. So, but I don't know in what context. I would need to look into it. Yeah.
Okay.
So, one more thing about this methodology. So, the timing is just the most important thing, right? Because I have thousands, millions of instructions, and I need one that I want to take. So, I think that's the also maybe one of the most impressive things, besides, as you said, that the chip doesn't power cycle, but I think it's pretty, yeah, interesting that you need to find this like needle in a haystack.
So how
And
does it usually work? You do it millions of times and then once it will work, or?
well, timing is relative, is what I say. So it means it depends from where we start our timing. If we start from boot, usually all these chips have a reset line that we can monitor and we can start counting from there.
Mm-hmm.
But this might be very long time between the boot and the instruction we want.
Mm-hmm.
So if that's maybe half a second, there's so much time that the jitter of the different clocks and the asynchronicity means we have a big window.
Mm-hmm.
Even
Mm-hmm.
if we know it's like in theory 10,000 instructions, counting that many instructions gets inaccurate because errors add up. So usually, yeah, sometimes you need to do that and you need to live with it. Sometimes you can find some pin or signal, which is my second point here,
Mm-hmm.
that switches later. So it switches state before the desired instruction, but later than boot. So if it's closer to the desired instruction, that's better.
Mm-hmm.
And then usually you need an experiment to find the correct delay or waiting time, except of course if you have firmware access or other types of information. Yeah. So if we do that by experimenting, by brute force in a sense, then usually we script a so-called fault campaign where we try different timings. So it's kind of guided brute force attack.
That's what I mean. Like you try a million times, and one of the
Yeah.
times you can hit the jackpot, or how is it?
Yes, I
Some
mean
people say it.
if you try every single instruction timing and then you reset every time, you will eventually get it.
Yeah.
But even there, if it's hard if it's too many instructions because mostly because sorry, I forgot what I wanted to say.
Because it will
Um,
crash in different places, and it may be hard for you to actually find out if
yes,
it was the right place.
yes. So because for one, because of yeah, because of jitter and stuff that's inconsistent between runs. And secondly, because you don't have 100% success probability. So even if you have the perfect timing, you don't glitch shift every time. So in my example, I have the correct timing and still it needs like 10 tries.
Mm-hmm.
So this means that I would need to
Oh, I
test every
understand.
timing. Yeah, I
It
would need
doesn't
to
need to happen
test.
every single time, even if you hit it
Yes,
correctly.
yes.
Mm-hmm.
That's correct. So that's something else. So if you have 10% probability and you need to try 10 different timings and all of them have to work, then it adds up. So yeah,
I understand now. Mm-hmm.
you want to have it as close as possible, your trigger, and then you want to have the delay as close as possible, or as small as possible, and success probability as high as possible. So that's why another reason why you would start with a development board, try to get your success probability high, um, and the timing later. So the physical parameters should be set as good as possible, and then you can transfer it to the real target.
Mm-hmm.
Yeah. Here I have some assembly. So that's why I didn't want to go into too much detail during the demo, because here we have what I call a infinite loop. And we can see here that there are different points where you can fold. So the first one is this test instruction, which is compare. So we compare a certain variable with another one. Then we have branch equal, which we can fold, so we can avoid the branch or we can jump to another location. And then we have the jump that goes back to the start. So all of these can be faulted and significantly change control flow.
And this is the code what you are running? Or this is just example
Let
code?
me check. I'm not sure right now, but yeah, no, it's not it because this has no add instructions. It's just an infinite loop. So this is just a loop where you get stuck.
And
For
you would like
instance,
to
let's
jump
say,
out.
yeah. So let's say I have critical code below here. Then yeah, then I want to glitch this instruction right here or the test instruction because the branch is not executed if the test executes correctly. Yeah.
Okay, I understand. Next.
So
Oh, you skipped the number
I have
7.
yeah, because it's another example. In this case, we have or and then branch not equal, and then a relative jump way later. So it's a different example. And we can glitch or instructions, we can glitch branch instructions, relative jumps, add instructions. So any kind of instructions almost can cause a change in control flow if you remove it. So assume you remove any of these instructions with a knob and assume how the control flow changes.
Maybe
Yeah.
we could explain a little because I don't know how many people actually they have assembler now. So maybe
Sure,
we can
sure.
explain a little bit what this means. Or
Of course.
so basically, instruction that's the smallest kind of command what, for example, microcontroller or processor can do. And in this code, the important instructions, I don't know, like the jump instruction, it says, or it's telling the code to jump on specific address, for example.
Yeah.
And if we can skip this jump instruction, it means the code will continue with the next instruction and it will continue with the next code.
That's correct. So in essence, assembly is human readable representation of machine code. And every time you write C code and you compile it for a microcontroller, it gets compiled into machine code. And this is a version that we can read of the machine code. And the reason why we look at this and not the C code, like shown here, is that all of this can be implemented in machine code in different ways. And it depends also on the platform and settings and optimizations. So something like this is a compiler could spot this. If you have the correct compiler settings, it will notice that debug enable is always going to be false and remove all of these 3 lines completely. And it will remove this as well.
Yeah, that's what I was thinking about because sometimes you can use the Pragma or how is it called? I don't remember, which will actually tell compiler like remove the pieces of code automatically if something is not set.
That's correct. So if you use C macros, then you can mostly ensure that these parts will not be in the firmware.
Yeah.
But what I want to show here is that even looking at your firmware through a decompiler, this is in this case I use Hydra, which is open source. You can look at your firmware and see if these checks and important code parts are gone, or if not. Because if they are still in your firmware, somebody could jump to it. So it's something good to do if you have critical stuff in your code.
And I think many microcontroller IDEs will actually show also the assembly code.
Yeah, if they do it, that's even better. Yeah.
Okay, next one.
So what I have here is just to show that there are different types of fault injection. So what I showed, which is very simple and also actually doesn't work on every target, that's important to say. So just because this works on the Arduino, it doesn't mean it works on STM, like not in this simple way. So maybe don't be too alarmed. But there are different ways. So you could do electromagnetic pulses, assuming we have a BGA chip. we don't have access to core voltage because it's underneath the chip. So, hey, we're safe, you know? But in reality, we have different ways. So, for example, we can use, yeah, electromagnetism from the outside of the chip. We don't even need to modify or touch it in essence. Then we could use lasers, or we could sometimes also work on the clock frequency. So if you have an external oscillator, you can maybe do something with that.
Laser, do you need to uncover the chip?
Yes.
Uncap, or
So
how's it
for
called?
laser,
Uncap?
you need visual like visual on the die. So you need to decapsulate it.
Ah, decap. Yeah.
And yeah, I think you had something on that
Yes.
already.
Yeah.
Yeah.
I created video on
Yeah.
similar topic, and it was a super cool video.
Yeah. So now you know why it's useful.
Okay. And clock frequency?
Well, yeah, I mean, it's less common, I would say. So I put it last. But if you can modify clock frequency of the device, for instance, if you can add your own clock, let's say you remove the crystal and you add a signal generator for the clock, then you can also mess with things. Because if you pause the clock, it might skip instructions, for instance.
Okay. Okay, let's go. I think you have
Yeah.
a little bit more details about
So
some of
yeah,
this.
I have something more about EMFI because that's what I do the most. And I mean, I think you're familiar with this law of induction, where if you run current through a wire, it will create a magnetic field. Now, what's important to know is that these circuits on the die of a chip also have like loops. So the transistors and stuff, we don't know exactly how they are wired, but usually there is some kind of curve or way of the current flow. And this means that any type of magnetism will get picked up again because it acts like a loop and it will create a current in the chip. So that's how EMFI works. You create a strong magnetic field, which then creates a current inside of the die of the target.
But it
And
has to
yeah,
be like
this
very
is,
localized, or because if you do it everywhere,
well,
then
yeah, that's a good question. So the magnetic field, of course, it has a shape and a size, and there's a lot of research on that as well. You can modify the size and specifically the size, for instance, through the voltage that you induce or that you inject into this inductor, basically, and also through the position. So we can see here that the probe tip is quite high, and if you imagine the magnetic field as a donut in a sense, you touch the chip only barely, then you don't affect as much area. If
mm-hmm,
you put it very low, you affect a lot of area
mm-hmm.
because more area is inside of the magnetic field or inside of the core of the magnetic field. And by moving it, you can, yeah, change how much area you affect. Or by changing the voltage. Yeah. So this is what it can look like.
And this is why
Mm,
we need CNC, because you need to know where it does something.
Yeah, with the CNC, we have a method of automatically moving the target or the probe, and we can automatically try different positions. That's the goal of the CNC because, yeah,
And you
we
can
we
repeat
move
it.
by yes, exactly. So we move by steps of 0.1 millimeter. Usually, look, it's what I did on this chip at least. And so even though the probe tip is pretty big, I think that's your question. This is a few millimeters in diameter, but it changes a lot if we move it over by just a hair. So zero point 0.2 millimeters, zero point 0.1 millimeters, it
Interesting. I
changes.
wouldn't say
Yeah.
that.
I have a slide about this in a minute. Because, yeah, other parameters for EMFI are the number of windings on the tip, the diameter, and the polarity. Because if we make a magnetic field that shows upside or downside, it also changes.
Mm-hmm.
Sometimes it only works if it's facing upwards or if it's facing downwards.
Mm-hmm.
So Yeah. Also the voltage, of course, timing is always critical, and then the position.
Mm-hmm.
And basically here, maybe it's also interesting. It shows how simple it is. So we have a capacitor, which is charged to some high voltage, and then we just have an IGBT that switches this voltage to this inductor or not. So you turn it off, charge the capacitor, turn it on, and you have a magnetic field. And actually, it's not the magnetic field that induces the current, but the change in magnetic field. So the turning on and off of this current on the inductor is what creates the glitches in the chips.
Yeah, because that's what inducts the currents inside of the chip,
Yeah,
the change.
yeah. So basically, if you have a pulse, so if you turn this device on and off again, you have kind of two times your induced current.
Mm-hmm.
That's also important to know. And yeah, so first of all, this is a bit of a teaser because yeah, um, it's not the full image. I don't know where it's gone. But first of all, yeah, the position on the die is very important. And usually we can scan a grid of positions like shown here and then color them in. If the height is bad, nowhere might work. So maybe you get everything crash. So you're too low to the chip and you're crashing everywhere because you're affecting too much of the chip. And no matter where you move, you're always affecting everything. And this is 2 by 2 millimeters. So you will, if it's too strong or the voltage is too strong, you will always just crash it. If you're too high, it's the same in reverse. So nothing will happen anywhere. And in this example, the chip was on a tilt. So the top left corner was a bit too high and the bottom right was too low.
Mm-hmm.
So this corner was always crashing and the rest was
Mm-hmm.
not doing anything.
Mm-hmm.
Yeah. And also every position must be tested repeatedly because as we talked before, we don't have 100% success probability.
Can you
Yeah.
damage chip this way?
I think you can, but it hasn't happened to me. It has only happened to me with voltage fault injection.
Okay. So basically,
Um,
when you tilt it, then you can kind of focus on specific area also. That
yeah,
can
but I
help.
would say it's harder to control because if I have it perfectly flat in relation to my EMFI device, then I can just use XY and don't touch Z axis at all. Um, but yeah, I will try to bring up a different image.
Okay.
Sorry for that interruption.
No, no, no. It's fine. It's very interesting. So I'm curious.
Mhm.
So this is what you normally do in school.
During my research at the moment, I use mostly this setup, the EMFI.
And
Um,
so you write some kind of papers on this topic, or why do you do this, or you are just interested in it? Or... Because you study at
um,
university. We didn't mention this, but you study at university,
yes.
correct?
So no, I'm working on my PhD right now,
Oh, PhD.
and yeah, I'm researching mostly countermeasures right now, actually. And because of that, I also need to have good attack setups to test my countermeasures, you know? So now we have something a bit nicer to look at. Um, all right. Yeah, let's check out, first of all, let's take a moment to look at the image on the bottom left.
Mm-hmm.
This is a system on package or a system on chip. And I choose this because you can see very clearly the different components. So inside of this one package, we have a BGA chip, CPU core basically. And then we have power management IC, memory, and everything has a different location, right? So if we don't open this, we don't know where is the core. And if we want to change execution, we need to attack the core. And therefore, we need to try all different locations. So this is on the right is an image from a fault campaign that I did. And we can see there is a one corner where it's yellow because only in this corner we can create faults. In all other spaces, we only find normal execution or crashes with these fine-tuned settings, of course. But even in this location where it's yellow, I get crashes sometimes. It's just that if you want to fault the chip, you need to do this in this area. Yeah.
Okay, I understand.
So if the chip is flat and your settings are dialed in, that's what you want to get. And then with this information, which you would usually get on a demo target again, then you can apply this on a real device.
And then you have to apply it at specific time or at the right time.
Yeah.
So you crash the instruction of what you want to crash.
Yeah, but the first step on EMFI is like an additional step. It makes it more complex. You first need to figure out where. This is like an extra effort to put in, but then you have a more powerful attacker model because you don't need access to the core voltage, which sometimes it's just not given.
So basically, you just need to find a place where you can create the fault.
Yeah,
that's it.
Yeah.
And then
the timing on top.
Yeah. Okay, I understand.
Yeah.
Okay. Next is the page which was at the beginning.
Yes, we started with this because this shows the whole setup. This was a close-up which we've shown before. We call this core device, the EMFI pulsar, is like the most important thing because this is what creates the high voltage and which creates these pulses that are precise and in size and in shape and in voltage and consistent so that you can work with it properly. This is chip shorter that you can just buy off the shelf. And everything else is basically open source. The CNC is it talks Gerbil firmware, I think. So it's almost like a 3D printer, takes the same commands. Then hardware reset module is something that I showed before, which I also put on GitHub. The delay generator is just an FPGA, which now I moved to the Raspberry Pi Pico. The one I showed before is the one that is actually running my experience now. And just monitoring with an oscilloscope. As you can see, this is way more precise also in terms of timings and voltages because they are analog. So, yeah.
So what you can buy, the EMFI pulsar, that's what you can buy?
Yeah, you can buy it. It's by New AE Tech. So it's online for sale.
So people are making this to exactly for this purpose, or there are also different ways how this can be used?
Usually, well, there are different ways. First of all, this one on the bottom left is an open source version. And there's the link for the website, which you can build yourself, and it's specifically made for this. But the big one I showed is basically a stronger version that's available for purchase and not open source. And there are different other open source options as well. And I'm working on my own of this as well, because this is only 200 volt, one single capacitor, and I'm working on something that's a bit stronger. So but these are specific tools. And then as you hinted, there are also ways to do it without specific tools that are sometimes even better. Like if you have a signal generator and an amplifier, then you can use a high voltage source and then basically, like really, how can I say, sophisticated attacks use high power power supplies and signal generators, and they don't use FPGAs and stuff like this at all. So they use dedicated lab-grade hardwares to get even more precise, usually because of the timings, but also to get a strong high voltage pulses for photon injection with electromagnetism. Yeah.
Okay, let's move to the next one. Oh, the 14,
So
14. What is on 14?
yeah, this was a video, but it didn't translate to Google Slides. If you want me to show it, I can.
I guess in the video you just show how it runs, correct?
Yeah, I can send you the video.
Okay, you can send me video, but I don't know if
Okay.
YouTube is not going to flag it. I can just put there some screenshots
Okay.
from the video, or you can explain what is in the video.
Yeah, so basically, the platform is moving around. It's not much, but it's visible because it's
Oh,
0.1,
okay.
0.2 millimeters, and then you can see the LEDs of the timings that go on and off. Because yeah, for every attempt it will blink and it will run, and you will see the pulse in the oscilloscope, the high voltage pulses, which are 500 volt, and then the trigger line above, and the pulse will move around due to the different timings. Yeah. So
15,
yeah,
15. Yeah. I don't
I'm
want to
just
skip
looking
any
what we
page.
have.
I'm curious. I'm only worried. I
So
hope your headphones will not discharge because this
no,
sometimes
it's fine.
happens.
No, it's fine. So yeah, I like EMFI because it's non-invasive and you can work on tiny targets like embedded devices. The PCBs are so cramped and the components are so close by each other that you cannot find a decoupling capacitor to hook into, or a trace to cut, or everything's VGA, or even like stacked chips. And it's hard to get to something physical. So this, you put it on top and you let it run. Disadvantages are higher entry cost. So this device I showed, the chip shorter, it costs, I think, 2,000 euros. And yeah, and if you want to monitor it, then you need the oscilloscope, which costs at least 500 euros. So higher entry cost, yeah. And also many parameters. So cost also in sense of time, because you need to invest a lot of time to find correct physical location. So yeah, these are some trade-offs.
I understand.
Yeah, what we showed before was voltage FI. And usually we attack not the supply voltage, but core voltage. I mean, it's supply for the core. So yeah, and many times what we get is an instruction skip or a duplication. With EMFI, since we have localized effects, we can position the probe above RAM or above register bank. And if we want to only affect registers, for instance, with voltage, we cannot really target what it's affecting. We can, I mean, sure, if we take core voltage, we affect the CPU core, but sometimes we could also lose register values there, and it's not as specific, but it's more likely that you get instruction skips. There's also sometimes instruction duplications. So you could get the same instruction twice because the core somehow stops and then it restarts, and the instruction is still in the pipeline and it gets executed again. And we have less parameters. We only have timing and duration. We can change the depth, so the voltage drops down to, but it's usually more hardware setup thing. So the way we set up the hardware, the MOSFET we choose, or if we use two supplies and we use an analog switch, we can of course set the secondary voltage. But usually that's something we don't script and modify up and down, but we set it once in a way that's fine for this chip, and then we just modify timings. So that's what makes it so nice and simple. And this is basically the whole setup. So what I showed before, this is what it really looks like. We have a glitch pulse signal from the attacker, the Pico is always the attacker in my case. And it just switches on and off this MOSFET, which acts as a switch and shorts vCore to ground. So yeah, I say you need to access the IC's core as close as possible. You don't want to drop the whole board's voltage because it will usually crash. Also, try to avoid voltage regulators because the voltage regulator will then take care of some dips. So the voltage regulator will make sure that your device has enough power. And if some chips have on-die voltage regulators, and then you need to make sure that you get the core voltage after this regulator and not before. Sometimes you need to remove decoupling capacitors. So in a sense, this
that's a
can
good
be
idea.
yeah, this can be a simple countermeasure in a sense. I mean, every attacker who has access to the hardware can remove them, but it makes it a bit harder, especially if you don't know which ones to remove. And sometimes if you remove too many, then your target won't run anymore because many chips don't run without decoupling capacitors, not properly. And yeah, basically what we are trying to do in general is violating operating ranges. So be it voltage, be it heat, there's also attacks that work when the chip is at a higher temperature. And yeah. I had another screenshot here. This is just a very long pulse. And in this case, it only drops to 4.7 volts. So even though it's more than half a millisecond or almost half a millisecond, it doesn't drop enough. In this case was because the MOSFET wasn't good. So I have some more information about this, but I don't know if you want to
No.
look
Okay,
into
yeah.
it.
I was actually thinking about what kind of MOSFET you use.
Yeah.
I was thinking like, oh, it's secret. He doesn't want to
No,
say.
no, no. I'm fine with sharing. So what I found out is that you want pretty low input and output capacitance because if you have capacitance, you have charge, and this will counteract the very thing we're trying to do. Drain to source resistance, also lower is better, usually like under 10 milliohms. Because if we go back to this, we want the power from the voltage regulator to go to ground as fast and as easily as possible. So we want as low as resistance as possible in this path. Also, of course, fast turn-on delay time and rise time, because otherwise, many times, if you inject a glitch pulse, which is very short,
Nothing will happen.
yes, let's say this is digital, what we see here in blue, and in analog world, what happens is I tried to draw, no. What happens in the digital world is we send 20 millisecond signal like this. And in analog, we get this. So especially with a microcontroller like this, they don't have strong GPIO outputs and they are not fast. So sometimes you even want a gate driver for the MOSFET just to be able to get really, really fast rise times.
So you need two
Yeah, lower is
transistors.
better. Yes, or a gate driver IC maybe. So yeah, there's some work for voltage fault detectors as well. I mean, this is a crowbar glitch because we like use a crowbar to connect voltage with ground. But the more you get into these attacks, you can do always more sophisticated and more. Just we usually do as much as necessary. Sometimes it just works like this, and then it's fine.
Because the circuit what we have now is very simple.
Yes, I really have essentially 100% this signal, nothing more, nothing less. This circuit, yeah. So what I found out is that yeah, this gate charge is also important. Gate charge basically, if it's too much from my understanding as a computer scientist, if it's too high, it prevents the MOSFET to switch quickly. So it's like a resistance. It doesn't want it to switch immediately if there's charge in it. I don't know if my understanding there is quite right, but that's how I imagine it.
Okay,
Yeah.
and package.
Yeah, so I found out that the best MOSFETs are usually in SMD packages for this application, but sometimes I find through-hole options, or at least DPAC, I think. Yeah, DPAC is what I used here. I just solder on some pins so that I can use it on a breadboard. And as you can see, they are pretty nice. They have gate charge of like 18 nanocoulomb or 39, which is inside my limits,
Mm-hmm.
and on resistance between drain and source of 5.7 milliohms or 3.1 milliohms. Um, yeah, and also sometimes it depends on the target. So some targets like a deeper glitch, as I showed before. Um, Here, parameters, depth, voltage it drops down to. So for some targets, you need a worse MOSFET that only dips to, in this case, 1.4 volts. Because if you have a better one that drops to 0 or 0.5,
It resets.
0.1 volts maybe, yeah, then it will reset even easier.
Mm-hmm.
So it's really about finding the sweet spot.
I was actually thinking about this when you were talking about this.
Yeah. Yeah, and I mean, other attacks that work on voltage use two power supplies and they switch between them.
Mm-hmm.
So the first one is regular 3.3 volts, and then the second one is like here
Mm-hmm.
1.4 volt.
Mm-hmm.
And the challenge with that is that you need access to the V-core and you need to cut it. So it's more invasive. Our attack here, we could actually just use a decoupling capacitor that's sitting here on top, and we can just solder a wire to it and perform this attack, remove it, and nobody's seen it.
Mm-hmm.
Yeah. So in general, what we want to script for voltage fault injection attack is the timing of the start. So when we want to start glitching, then how long it should be. So for how long do we remove the power? And then we always start a bit earlier because we don't know if our timing device is a bit too fast for the target. So we start a bit earlier to be sure. And then we sweep across a reasonable range of timings. So if we know we have a good trigger signal and it's not thousands of instructions, we start a bit earlier and then we try maybe 10, 20 instructions later and earlier, because this is like in the realm of possibility, and that we are not perfect and therefore we need to sweep. As I said, it's about clock drift, inaccuracies, delays, especially also in the code of the attacking device or in the code of the target device. Think about devices that have multi-cores with scheduling, so multi-threaded execution. So something unexpected could also happen, and then you could have to retry.
Mm-hmm.
And so you never get 100% success. And so it's, yeah, about educated guessing, using side channels, firmware dumps if you have them, brute force if you need to, and trying educated guessing, yeah, is the best way to put it, I would say.
Okay, I understand. I understand.
Yeah. And on the hardware side, so this is all what you can do in software. And on the hardware side, you should look at the depth of the glitch voltage. You can measure it with a logic analyzer if you have a nice one,
What do you
like
use?
shown here.
Which one do you use?
It's the Saley Logic Pro
Mm-hmm.
16 or 8. We have both. And they have analog measurement, which is nice because, I mean, you could also use a scope which has digital measurements, but I like having both in one tool so that I can have in one interface my digital signals like trigger, reset line. I want to monitor all of this stuff. And at the same time, I want to look at the core voltage, see if something weird is happening or if my glitch is bad. If a wire got loose, you immediately see that the glitch is not perfect anymore. So if anything's imperfect, you can spot it. And yeah, lastly, for getting a faster or slower glitch, in a sense, you might need to reduce capacitance or add capacitance or resistance even manually. And yeah, if you get too many crashes, for instance. Or if you cannot glitch the target, then you need something faster or deeper.
That's
So
interesting. Yeah, because
you
I
always
wasn't
need to
thinking
measure
about this.
and yeah. So it looks simple, right, from my initial demo, but in reality, a lot of work went into fine-tuning all these cable lengths, finding the right MOSFET for the correct depth of the voltage and so on. So it's still a simple setup and a simple attack in the context of things, but there are a lot of consideration. Yeah.
Okay, next.
Here's another negative example in a sense. We can see that voltage over 9 milliseconds is dropping really slowly. So this almost really looks like a capacitor that's discharging. I think this was from actually this was from a board that had all the decoupling capacitors still attached, and they were so strong that it took multiple milliseconds to discharge, and therefore we could not glitch it without removing them.
Mm-hmm.
So that's why I highlight reduced capacitance. And here, yeah, this is really nice to show the difference between MOSFETs.
Mm.
Yeah, so here we have the same pulse. Pulse is the signal coming from the Raspberry Pi Pico.
That's the
So
gate.
in digital world, it's the gate signal. We have the same length. Um, don't get confused by D7. I will say something. But here's the voltage. That's the interesting part. So one MOSFET gives me a shallow glitch to 2 point something volt, and the other one is way deeper. But then it jumps up afterwards. So it's with some ringing. And I believe that in this case, the one on the left even worked better than the one on the right. So even
Wow.
though it looks worse because this one is too deep, too fast, even if I do it shorter, then it's too short. It doesn't affect the instruction properly. And the edge maybe, also this edge is maybe too strong and it can also get a glitch because as we said, well, this would be in EMFI with the edges, but even here, if we have a spike of voltage, it can also glitch the chip because they don't like it. What we see here is funny because this is a bug in the logic analyzer in a sense. Basically, I think that the voltage switching couples into the digital signal of the trigger,
Mm-hmm.
and it probably in the analog world it only has a small dip here, but it gets picked up as a low
I
signal.
understand.
So yeah, and here it's just a line, but yeah. So even here with this tiny glitch, it even here it creates interference in the logic analyzer. So it's stronger than you think. Yeah.
It's because when I was experimenting with this logic analyzer, then I found out you need to be very careful about the wires because usually they have long wires, and these wires can be tricky when you are doing these kind of measurements. So
Yeah, absolutely.
I ended up using much shorter wires. I think the original ones, then it was working. The measurements what I was doing, they were working. But I also used longer one, which were delivered
Hmm.
with some kind of probes, and these
Hmm.
didn't work.
Yes, that's very possible. Like it's pretty common actually, I would say. Yeah, that's good to know.
And the last one, there is the
Yeah,
last one.
last one is just if you want more information, I work at CMO, it's a department at the Technical University of Darmstadt, and we work on secure mobile systems. And my focus is on hardware attacks, volt injection, and countermeasures in particular. So if you have questions, you can contact me. And if you have more questions, we can also go to a earlier slide.
I don't have any other questions.
Okay.
I would like to thank you so much, Dave, for this, and also, you know, preparing all the materials and spending time preparing the demo. And I'm very happy you created also the demo, because I always like it to see real demonstration, just comparing to just going through slides. It's always the best.
Yeah, thanks for having me. Thanks for the opportunity.
Okay, I learned a lot. I'm really very curious if there are any comments from people who are watching this video. So everyone who is watching, don't forget to leave comments. I really would like to know what everyone think about this, and if they ever like if they were ever thinking that this can happen and this is the way how actually we can influence what is happening on the chips. Because before I talk to you, I know I created similar video on this topic where we touch this,
Mm.
but before I had no idea we can do something like this.
Yeah,
So thank you so much, Dave, again.
thanks.
That's all for this video. I hope it was helpful. If you would like to learn more about electronics and board design, check out our online courses. You will find everything important there, from basic board design up to advanced board design and high-speed PCB layout. We have courses in Altium, Cadence, KiCad, and also courses covering many different topics, for example, FPGA, EMC measurements, and so on. Visit our website at fedevel.com. That's all for this video. Thank you very much for watching, and don't forget to leave your comments. See you in the next video. Bye.